Functions of several variables. Part A. Domain and range of functions of several variables. Learners who have completed higher secondary course are familiar with the definition of real valued functions defined over subsets of real numbers, their limits, continuity and differentiability. We can think function as a computer program that takes an input x, operates on it in some way and produces exactly one output f of x. For example, if f of x is equal to x cube, the input 2 gives the output 2 cube is equal to 8.
In this session, we extend this to real valued functions defined over subsets of Cartesian product of real numbers. We discuss domain and range of functions of more than one variable in this session. Graph limits, continuity and differentiability of functions of more than one variable will be discussed in the coming sessions. Functions of more than one variable occurs in real life. For example, to model varying temperature in a large region, one can use a function which takes on two variables, longitude and latitude, maybe even altitude as a third, and output one variable, the temperature. Suppose we consider the temperature T that depends only on two variables, longitude and latitude, which are denoted by L1 and L2 respectively. Then T is a function of two variables L1 and L2, which we denote by T is equal to f of L1 L2. F is some complicated function that determines which temperature each longitude-latitude pair corresponds with. Formally, let's begin with the definition of real valued function where the domain is a set of n tuples. That is, the domain is a subset of the Cartesian product r cross etc. cross r n times, which is equal to the set of all n tuples x1, x2, etc. xn, such that xi belongs to R where I from 1 to n. Suppose D is a subset of the set of all n tuples of real numbers n tuples x1, x2, etc. xn. That is, D subset of R cross etc. cross R n times. A real valued function f on D is a rule such that to each element n tuple x1, x2, etc. xn in D, there corresponds a real number w that satisfies the equation w is equal to f of x1, x2, etc. xn. We say that f is a real valued function of n variables x1, x2, etc. xn. This set D is the function's domain. The set of w values taken on by f is the function's range or image and is denoted by range of f or image of f. That is, range of f is equal to image of f is equal to the set of all f of x1, x2, etc. xn such that the n tuple x1, x2, etc. xn belongs to D. The symbol w is the dependent variable of f and f is said to be a function of the n independent variables x1, x2, etc. xn. We also call the variables x1, x2, etc. xn the function's input variables and call w the function's output variable. Instead of the variables x1, x2, etc. xn, variables such as x, y, z, etc. or a, b, c, etc. may be used if they are appropriate to the situation. For a given n tuple x1, etc. xn, we call f of x1, etc. xn function's value at the point x1, etc. xn. For example, the value of f of x, y, z, which is equal to square root of x square minus y cube plus 3z at the point 4, 0, negative 4 is f of 4, 0, negative 4, which is equal to square root of 4 square minus 0 cube plus 3 times negative 4, which is equal to square root of 16 minus 0 minus 12, which is equal to square root of 4, which is equal to 2.
To understand this, think of a function as a computer program that takes an input triple xyz, operates on it in some way, and produces exactly one output f of xyz. For example, the input triple 4, 0, negative 4 gives the output 2.
We now discuss the natural domain of a function. We know that if a function is defined by a formula y is equal to f of x and the domain is not stated explicitly, then the domain is assumed to be the largest set of x values for which the formula gives y values. This is the function's so-called natural domain or simply domain. Thus, the natural domain of a function given by an equation is the largest set consisting of all points where the definition of that function makes sense or valid. Now, we use this idea in the case of a function of n variables. Suppose a function is defined by a formula w is equal to f of x1, x2, etc. xn and the domain is not stated explicitly. Then the domain is assumed to be the largest set of n tuples x1, x2, etc. xn values for which the formula gives w values. This is the function's so-called natural domain. Hence, if the domain of a function is not defined explicitly, then its domain is obtained by excluding inputs that lead to complex numbers or division by 0. This is illustrated in the following examples. Z is equal to positive square root of 7x raised to 4 plus 5y square is a function of two independent variables x and y. Hence, it is a function of two variables and hence its natural domain is a subset of the plane R square. Since square root of a negative number is imaginary, it follows that the function is defined only for those ordered pairs ordered pair xy for which 7x raised to 4 plus 5y square greater than or equal to 0. Due to the presence of x raised to 4 and y square, we have 7x raised to 4 plus 5y square is always non-negative for any choice of ordered pair xy. Hence, the natural domain is D is equal to the set of all ordered pairs xy where x and y belongs to the set of real numbers. That is, D is equal to R cross R, which is equal to R square. As another example, consider the function z is equal to square root of 1 minus x square minus y square. We note that z is a real number only when 1 minus x square minus y square greater than or equal to 0. That is when x square plus y square less than or equal to 1. So, D is the set of all ordered pairs ordered pair xy in the plane such that x square plus y square less than or equal to 1. That is, D is equal to the set of all ordered pairs ordered pair xy belongs to R2 such that x square plus y square less than or equal to 1. That is, D is the set of points in the disk with center at the origin and radius 1. As another example, consider the function z is equal to 1 upon x cube minus y cube. Since x cube minus y cube is equal to x minus y times x square plus xy plus y square, it follows that z is equal to 1 upon x cube minus y cube can be defined at all points ordered where xy in R2 where x not equal to y. Hence, the natural domain of the function is D, which is the set of all ordered pairs x, y belongs to R2 such that x not equal to y. That is, the natural domain is the set of all points in the plane that do not lie on the line x is equal to y. The natural domain partitions the plane into two by the line x is equal to y. We know that the natural domain of the real valued exponential function f of u is equal to e to the power u of a real variable u is the set of all real numbers. With this in mind, we note that the natural domain of the real valued function g of u is equal to e to the power negative u is also the set of all real numbers. With this information, let's discuss the natural domain of the function of two variables h of xy is equal to e to the power negative x square minus y square. We note that e to the power minus x square minus y square is equal to e to the power minus x square plus y square. We have x square plus y square is always a real number for any choice of ordered pair xy. Hence, for any choice of ordered pair xy, the function h of xy is equal to e to the power minus x square minus y square gives a value. Hence, the natural domain D of the function h is the set of all points in the plane. That is, D is equal to r square, the plane itself. As another example, we consider the function z is equal to f of xy, which is equal to log x plus log y. The function can be written as z is equal to log xy. As the real valued logarithmic function of a real variable is defined only for positive real numbers, log xy is defined for those ordered pair xy for which xy greater than 0. Hence, domain of z is the set of all points in the plane with the product xy strictly greater than 0. That is, D is the set of all ordered pairs xy in R square such that the product xy greater than 0. That is, the domain is the set of all points in the first and third quadrants excluding the boundary by x and y axis. As another example, we sketch the natural domain of the function f of xy is equal to natural logarithm of x square minus y. We know that the domain of the natural logarithm function is the set of positive real numbers. Hence, the function f of ordered pair xy is equal to ln of x square minus y is defined only when x square minus y strictly greater than 0 or x square strictly greater than y or y less than x square. We first sketch the parabola y is equal to x square as a dashed curve. To identify the domain, we choose the point ordered pair xy is equal to ordered pair 0, negative 1, and note that negative 1 is equal to y strictly less than 0 is equal to x square. Hence, the region is the one that contains the point ordered pair 0, negative 1 and with the boundary y is equal to x square. The region y less than x square consists of all points below the curve y is equal to x square and is the natural domain of the given function. As another example, the natural domain of the function f of xy is equal to square root of y minus x square is the shaded region in the figure, including the boundary by parabola. We now list the natural domain and range of some functions of two variables in the following table.
Because square root function is defined for non-negative real numbers. The natural domain of f of xy is equal to square root of x square minus y is the set of all ordered pair xy for which x square minus y greater than or equal to 0. And such a set is the set of all ordered pair xy for which x square greater than or equal to y. Range of f is the set of values w for which w is equal to square root of x square minus y. The possible such w is the set of all w such that w greater than or equal to 0. So the range is left closed right open interval 0 infinity. The function f of xy is equal to 1 upon x square plus y square is not defined when x square plus y square is equal to 0. We note that x square plus y square is equal to 0 if and only if x square is equal to 0 and y square is equal to 0, and that is if and only if x is equal to 0 and y is equal to 0. That is, f of xy is defined everywhere except at the point ordered where xy, where ordered where xy is equal to ordered where 0, 0. So, the natural domain of 1 upon x square plus y square is equal to the set of all ordered where xy such that ordered where xy not equal to ordered where 0, 0. It can be seen that 1 upon x square plus y square never gives a negative value and never gives 0 value, but it gives positive values. So, the range of 1 upon x square plus y square is open interval 0 infinity. We know that the trigonometric function cosine function has the natural domain the set of real numbers. Here our function of two variables is cos xy, and here we have the freedom to choose any ordered where xy such that the product xy is any real number. So here we have the freedom to choose any ordered where xy. So the domain of cos xy is the entire plane. From calculus class we know that the trigonometric function cosine function has the range closed interval -1, 1. So here also the function of two variables cos xy also has the range closed interval -1, 1. Graphs of functions of two variables will be discussed in the next session. Thank you for watching. Have a nice day.